Math 2414, improper integrals, two types of improper integrals. To wrap up this chapter on techniques of integration, we're going to look at some definite integrals that have some issues. Namely, issues with the limits of integration, the interval over which we're integrating these functions. There are two specific types of improper integrals we'll be looking at. The first are integrals with infinite limits of integration. For example, let's say that we wanted to evaluate the integral from 1 to infinity, whatever that means, of 1 over x squared dx. Or maybe we just wanted to evaluate the integral from 1 to infinity of 1 over x dx. Both of these do have a geometric interpretation. We're just finding an area. And the graphs are fairly similar. For example, the graph of f of x equals 1 over x squared has a branch in quadrant 1 and a branch in quadrant 2. They're both above the x-axis because naturally the output's going to be positive. And there's a vertical asymptote right down the middle. But if we were only integrating from 1 to infinity, we would start at 1, and we would be trying to calculate the area of this infinitely long lamina, if you will. Or the same thing if it were f of x equals 1 over x, which you're probably a little more familiar with, has a branch in quadrant 1, but also in quadrant 3, because for this function, negative inputs yield negative outputs. And if we were to find the area from 1 to infinity, or rather the integral from 1 to infinity, we'd be calculating that area. So it's a natural question to ask, what does it even mean for that area to exist? It goes on forever. Well, would you believe me if I told you that one of these laminas does, oh, I'm sorry, I'm using a word you may not be familiar with. Lamina. Lamina is just a fancy name for a generic shape, a generic flat surface, that's all. But would you be surprised if I told you that one of these laminas actually has a finite area and the other one doesn't? And what does that even mean, and how do we determine that? Well, we're going to answer all that in this series. But that's one type of improper integral where you have an infinite limit of integration. And by the way, the infinity can also be on the lower limit in the form of negative infinity, and both limits can be infinite. It's not unreasonable to talk about an integral like the integral from negative infinity to infinity of x times e to the negative x dx. So that's one type of improper integral. The other type of improper integral is where we have a discontinued limit of integration. And really I shouldn't say discontinuous limit of integration. Let me phrase this a little bit better. F of x is discontinuous at some point, at some value in the interval of integration. What does that mean? Well, let me show you. For example, let's say we want to evaluate the integral from 0 to 4 of 1 over the square root of x dx. If you'll notice, the function we're integrating is discontinuous at 0 because it causes the denominator to equal 0. But does that mean that this integral doesn't exist? We'll answer that soon. Or maybe I'll have something like the integral from 3 to 5 of 1 over the, I don't know, let's just say 1 over x minus 5. Which would be discontinuous at x equals 5 because that causes the denominator to be 0. But it doesn't just have to be discontinuous at the lower or upper limit of integration. It could be discontinuous somewhere in the middle. For example, if we had something like the integral from, let's just say from negative 2 to 2 of 1 over, let's say cosine of x minus 1 dx. That looks fairly harmless. but when x is equal to 0, which is between negative 2 and 2, cosine of 0 is equal to 1. 1 minus 1 is 0, and that causes a problem. So that's the other type of improper integral, where the interval over which we're integrating contains a value that the function we're integrating is discontinuous. And how do we tackle all of these? Well, that's what we're going to figure out in these next videos.